So indeterminate forms and L'Hopital's rule is kind of a fun application of limits, in my opinion, and it's going to be the last kind of technique that we learn involving limits. And the idea is that when we've been evaluating limits, the goal usually is that we have the limit as x approaches something, and then here we have some function. But sometimes we've seen that, kind of depending on what happens, maybe we get a number out, right? That's the dream. But sometimes you may notice that we've gotten some where we divided by 0, like in the last video, and we try and do some algebra to kind of, fix this problem. But we can also get things like, for instance, if I have the limit as x approaches infinity of e to the x over x squared, if I were to just plug in infinity to both of these, I'm going to get e to the infinity over infinity squared, which is infinity over infinity. And before you sit there and try and argue that this is equal to 1, I'm going to tell you that this is not equal to 1. Okay, it could be, but it's probably not equal to 1. And you're like, well, what do you mean? Well, I did publish a video on this talking about the different sizes of infinity and that they exist and things like that. So if you're curious, go check out the video on limits and infinity. But the point being here is that let's kind of consider both of these graphs for a second. Okay, let's consider these. Now, both of them do indeed go to infinity, right? That's what, if we plug in x is infinity, that's what this part of the limit, is telling us. It's saying, look, the top e to the x is heading off to infinity, and x squared is heading off to infinity. All right, and so the question is, how on earth would I evaluate this limit all together? Okay, right? This thing is as one single function, where is it going? And this is kind of a tricky question, but I think it's not so bad, and this is probably the most important part of the entire video, so pay attention. You have to remember that a fraction is just a comparison of two things, right? A fraction like 1/2 says that maybe I've got 4 coconuts and the other person's got 8 coconuts. So I have half the number of coconuts that the other person has, right? And the idea here is that basically what this limit is asking us to do is it's saying, look at where this function's going in the long run. Look at where this function's going in the long run. Put it together and tell me where is the whole thing going in the long run. Okay, that's the idea. But the problem is that if I look at the long run for both of them, they both seem to be going off to infinity. But if you want to view, infinity as like this giant ominous cloud, it's a much more interesting question to say, well, who's getting to infinity first, right? Because if e to the x is going up like this, and then x squared is just taking its sweet, sweet time, then this ratio is probably also going to be infinity when I evaluate this limit. Right? If the top thing is growing way faster than the bottom one, then in the long run, this one's already going to be like hitting infinity more or less, while this one's at the number 10 or something like that. And vice versa, if this limit was flipped around, right? And I have x squared over e to the x. And you say, okay, well, I know e to the x is exponential, right? E to the x is an exponential function. This one grows insanely fast. And it definitely grows faster than x squared, right? Just as kind of like some intuition, we would have, maybe an idea that even though x squared is going off to infinity, and even though e to the x is going off to infinity, that this limit here is going to be 0, because the bottom is going to get to infinity so much faster, and the top is just going to be dilly-dallying on its way. And so when I'm doing a comparison and saying, look, in the long run, like which one of these is bigger, we have an idea that, okay, e to the x is going to kind of take over and kind of dictate what the value of this ratio is going to be. And so the question is, how do we actually show that mathematically? And so this is kind of an interesting thought. The idea is that if, when we look at this limit, right, if I look at this particular limit, this is a comparison of y values. This is saying, look, the y value of e to the x is going off to infinity, and the y values of x squared is going off to infinity. But the thing that we're actually interested in, and what math is going to tell us, is if if the y values are going off to the same thing, right? If they're both going off to infinity, what we want to look at instead is the rate at which they go off to infinity. And what I mean by that is, again, if I have two functions, right? I'll move my cloud over here. Okay, so let's pretend that infinity is over here. Okay, if I have two functions and they're both kind of making their way off to infinity like this, right? And they're both going, right? This first one has a slope of 2, and this second one has a slope of 2. If they're both going off to infinity at the same rate, then if I'm looking at the limit of whatever this white function is, and I'm comparing it to the limit of whatever this bottom function is, and I'm saying, look, what is this ratio going to be in the long run? It would make sense to say, look, they're both going off to infinity, but we can't evaluate infinity over infinity. We can't do this, technically speaking. So instead, we kind of look and say, well, let's look at a limit of their slopes, right? Let's see which one is growing faster. And because in this particular case, they're both growing to infinity at the exact same time, the idea is okay, well, then they're both going to reach the same infinity at the same exact time. And so we can just say, so we can just look at the ratio of their slopes and say, there's like a 1-to-1 ratio. There's a 1-to-1 correspondence in the long run, right? And our limit here is going to be 1. Likewise, if this purple one, say grows much faster, right? If we say that the slope of this purple one is really steep, right? It's like 10 or something. We could say, well, okay, they're both going to infinity. But the slope of this g function, is 10, and so we'd say, okay, so in the long run, the white one's growing at a rate of 2, whatever our unit is, but the pink one's growing at a rate of 10, whatever our unit is, and because the pink one's growing faster, you can kind of see it here that the ratio we would expect to these y values in the long run is going to be 1-to-5. And that's simply just due to the fact that, we can look at the slopes of these functions instead and make this comparison. And so I'm going to now, with that intuition kind of under our belt, introduce you to indeterminate forms and L'Hopital's rule. So, definition. Okay. A limit evaluates to an indeterminate form if it equals one of the following. If it equals 0 over 0, infinity over infinity, right? 0 times infinity, infinity minus infinity, and basically comma 0 raised to the infinity. These are all, sorts of math that we cannot actually just readily, willy-nilly be like, oh yes, the answer is, to look at infinity over infinity, be like, the answer is 1. It's not, right? 0 times infinity, that's even more of a brain-breaking thing to think about, okay? So these are all indeterminate forms. And the idea is that if our function, right, if whatever it is that we are trying to evaluate the limit for, evaluates to an indeterminate form, then we get to use a brand new tool to help us evaluate this limit. And so I'm going to give you one more definition, which is called L'Hopital's rule. So maybe it's not a definition, it's a rule, L'Hopital's rule. And L'Hopital's rule is as follows. It says, if the limit as x approaches something, and we're going to say of some function, right? So we're trying to evaluate some limit. Usually this is a rational function. And actually, let's just keep it that way. Instead of saying usually, let's just keep it that way. So we're just going to say if we have the limit as x approaches a of the ratio of two functions f of x over g of x, and this evaluates to indeterminate form. Okay, indeterminate form. If this limit is indeterminate, then we can instead look at the limit as x approaches a of f prime of x over g prime of x. Okay, and this should make sense again, right? I'm going to go back to this drawing. The idea is that, look, if if these things go to the same number, 0 over 0, infinity over infinity, then the next thing that we want to do is say, okay, well, how quickly do they get to that same number? And it's like, oh, well, if one of them is going much slower than the other one, but it's only like they're just off by, a little bit, like some multiple, like 1/5, we'll say, oh, yeah, okay, well, in the long run, this ratio should be about 1/5. It makes sense. Okay, and so this is L'Hopital's rule. This is when we can use it. And I guess I'll just kind of show you a quick example of something that's where you might see this. So, for example, you might get, evaluate the limit as x approaches 0 of sine of x over x. Okay, what value do we expect the ratio of these two functions, sine of x and x, to have in the long run? Because, sine is going blah, 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 and this thing is a straight line, right? And we're, if we're thinking about the values of what this is, sine kind of goes, sine of x kind of bounces between -1 and 1, right? And then this thing's supposed to be 0, right? How do we evaluate this thing? And so our first thing that we would try is we'd probably try and just plug in 0. But if I plug in 0, I'm going to get sine of 0, which is 0, and in the denominator I get 0, and this is indeterminate. And so we'd say, okay, well, at x is 0, we expect both of these things to approach 0. The top and the bottom each approach 0. And so the next thing we're going to look at is the rate at which they approach 0. And so we're going to say the limit as x approaches 0 of the derivative of the top, which in this case is cosine of x, and the derivative of the bottom, which is just 1, is going to give us the same correct answer. And now I can plug in 0 because cosine of 0 is just 1, so I get 1 over 1, which is just 1. And so what this means is that both of these graphs basically approach 0. Sine of x approaches 0 and x approaches 0 at about the same rate in the long run. And so that means that the limit of sine of x over x is just going to end up equaling 1. And, maybe I'll do the example that I showed earlier, which is, the example of the limit as x approaches, we'll say, let's do x approaches 0 of e to the x. Do we want to do 0? Let's do infinity. Limit as x approaches infinity of x squared over e to the x. And again, if I just plug in infinity here, I'm going to get infinity over infinity. This is indeterminate form. Okay, and so we're going to look at the slopes of these. Now, as you do more of these problems, you actually can get really good at figuring out what the answer is going to be without even doing any heavy lifting. Because like I said before, yeah, both of these are going off to infinity, but we should know that exponential functions go to infinity way faster than just a regular polynomial. And if you don't believe me, plot it on Desmos, right? Seeing is believing. But we're just going to use L'Hopital's rule, and we're going to say, okay, so I can just evaluate the limit as x approaches infinity of 2x over e to the x. Now, this is still indeterminate, and so we can do it again, right? We can treat this as a brand new problem and take the derivative of that. And so we're going to get the limit as x approaches infinity of 2 over e to the x. And finally, we're going to get 2 over infinity, which is 0. And so lo and behold, right, the answer that we kind of had an idea of is that the denominator here is going to approach infinity way faster than x squared does. And sure enough, that shows up in the fact that the answer using L'Hopital's rule tells us that this limit is going to be 0. And if you were to plot this graph somewhere, and if you were to plot it, you would see that in the long run, no matter kind of what's going on, that in the long run it is dying down out to 0. So this is kind of a fun idea, right? And so what is, like, if we were to talk about the size of sine of x and the size of x at x is 0, right? You're like, okay, which one of these is bigger? Which one of these is more crazy? It's just like a little fun thing you can do in the side of your head to kind of create a catalog where you're like, oh, well, exponential functions are way bigger than polynomials. Trig functions aren't really that big compared to exponential functions or big polynomials like x squared, x cubed, things like that. It's just kind of fun to kind of build your own catalog, and you'll start to learn, if I were to ask you which of these functions, e to the x, ln of x, sine of x, x squared, right? All these functions that we've come to learn and use, right? Square root of x, which one of these is the biggest, right? Which one is the second biggest? Which one's the third biggest? And answering questions like these limit questions and really just trying to build that intuition is a good way to kind of shortcut some of this work. But worst comes to worst, we can just use L'Hopital's rule and evaluate it just like so. So that's going to do it for this video. L'Hopital's rule, indeterminate form, all wrapped up. We've only got one more, and it's kind of the whole build-up, the culmination of this entire course, which is to define the derivative in the first place. And so if you're ready to tackle that, head on over to that video.